This presentation was originally given on May 1st, 2010 to the Oregon-Washington Regional Mensa Conference. The first 5 minutes or so are a patch because someone forgot to turn the camera on. There have been two roads to a theory of intelligent design in the West. One road was through Jerusalem by means of revelation, the other through Athens by means of reason. This talk is almost exclusively about the latter, the path of reason. The title, The Other Theory of Intelligent Design, distinguishes what is to be presented here from the semi-popular stereotypical creationist theory that relies on an external supernatural being. As you will see, the other theory of intelligent design proposes a largely self-contained, self-developing universe, although in the final analysis, perhaps, this doesn't preclude some relationship to something external. The strategy of the talk is to outline a shift from one way of understanding the world and our place in it to another way of understanding the world and our place in it. It's important that to a very large extent, the shift is not driven primarily by new evidence. The best analogy is with the Copernican revolution, where we moved from understanding the motions of the sun, moon, planets, and stars in one way from an Earth-centered perspective to understanding the same observations from a different sun-centered perspective. The key point about this shift from the Earth-centered to the sun-centered view is that the evidence, the observations, are largely the same, just organized differently. I also like to represent this shift in perspectives as a turn, as you'll see, rather like a 90-degree turn from one perspective to another. The idea that this shift to a theory of intelligent design might be represented as a turn goes all the way back to Plato, where in his famous dialogue, The Republic, he expressed it as involving a, quote, turning of the soul, unquote. The turn, as I'm going to outline, then is from one way of understanding ourselves and the world to another, from one way of making sense of the world and our place in it, from one coherence to another. One overall theme here, a reflection really, is that the turn, as I will represent it, isn't new. There's an ancient version and a modern version. And I think it's valuable to link them in that each tends to illuminate certain aspects better than the other. In both the ancient and modern versions, the turn is roughly from the scientific approach, the scientific research program, trying to understand reality as entirely physical and impersonal, governed by universal laws of causal necessity, to, on the other hand, the intelligent design research program, trying to understand reality as animate and developing, something like a conscious organism. For instance, Aristotle seems to suggest that the universe develops rather like a child grows up and matures. The other fundamental difference between these two approaches, these two research programs, is captured best, I think, by an image suggested in the modern era by John Dewey. Dewey characterizes a scientific approach as a spectator approach. The way I like to set this up, imagine we find ourselves here in the world, don't know how we got here, where we are, what time it is, or what we're supposed to be doing. It's getting a little boring. So someone suggests that just for something to do, we try and figure out how the universe works. Now, as Dewey points out, it's important that our inquiry, our enterprise to figure out how the universe works, doesn't itself change how the universe works. If our activities change how the universe works, then we have a serious, perhaps fundamental problem. Slightly different formulation of this implication of the spectator enterprise is that the nature of the universe, how it works, must remain constant, fixed in time, if our inquiry is to be able to converge from our initial ignorance to a final, complete understanding. Theory of everything. The nature of the universe must remain the same, fixed over time, space, in order for the spectator research program to succeed. The nature of the universe must be space-time invariant. Dewey's spectator image has also been referred to in the modern philosophy of science literature as the detached observer framework. Dewey contrasts the spectator approach to understanding reality and our place in it, to the participant approach. In the participant approach, one begins with the presumption that our actions do change the nature of the universe, basically simply because we are part of the developing universe. Dewey's proposed shift from the spectator to the participant perspective is a modern version of the turn. It's what I will refer to in the modern version as the pragmatic turn. Perhaps needless to say, the problem of understanding reality and our place in it is rather different in these two approaches. Finally, I want to spend some time on the Stanford economist Paul Romer, who represents the turn in modern economics from a detached scientific economics to a new participatory developmental economics. Romer's turn illustrates how we might understand an inherently developmental participatory system, providing an important analogy for both biological and cosmological evolution. Romer points to how a system might continuously reorganize itself, intelligently bootstrapping itself, progressively, constructively. Romer gives us insight into the process of intelligent design as a creative, participatory evolution of life and the cosmos. So let me start by looking briefly at the Socratic turn. Socrates, the philosopher of Plato's dialogues, is not normally thought of as a scientist, although in the dialogues he regularly expresses respect for scientific knowledge, seeing it nonetheless as inherently limited. But after his famous trial, literally on his deathbed, he recounts that as a young man, perhaps into early middle age, he was really an enthusiastic scientist in the tradition of the best ancient Greek science, the tradition starting with Thales and Anaximenes and Anaximander, associated with Parmenides and Pythagoras. Then he made a fundamental shift, the Socratic turn. In part, this came from a frustration with what he came to believe was a fundamental ambiguity about the scientific notion of causal necessity. He seems to have come to the conclusion that the whole attempt to discern this causal necessity, the spectator enterprise, to find the laws that ruled the universe, was somehow fundamentally misguided. Xenophon, a friend of Socrates and one of the main commentators on his life, talks about the very day that Socrates turned. The turn was from trying to understand how the world works, the spectator enterprise, to trying to understand how to work the world, how to work in the world, a participant enterprise. Xenophon mentions that the conversation that day had to do with household management, managing a family enterprise, like a farm, a family with children, the whole system, the holistic system. In one of Plato's dialogues, the Gorgias, Socrates asserts that the most important, the most fundamental question of all is how should we live? This question applies to the individual, the family, the larger community, life as a whole, and perhaps to the whole cosmos viewed as an enterprise, the enterprise of the development of life. This is the question that is fundamental to the participant perspective. How should we live?
The question, how should we live, I'm going to argue is in fact a design question. So it's like, how should we design the irrigation of our fields? How should we design our houses? How should we design our neighborhoods? How should we design our cities? How should we design our agricultural system? How should we design our economic system? How should we design a political system that will preserve the economic system that we want? These are all design questions. They're all questions of how should we live, all right? So I'll get you a sense of linking those two. This problem of how should we live, which is fundamental, which I'm going to push for, is equivalent to this question of how should we live. And this is what in Socrates and the Gorgias says, this is the most fundamental question. The question is, how should we live, all right? Now, in the modern era, this same move has been made, and you can trace it. The American pragmatists were into it. They talk a lot about Darwin being important, and it's not just Darwin. It was what was in the intellectual milieu at the time, which was a this obsession, all of a sudden, that the universe actually evolved, that things actually changed, that the world wasn't fixed. It isn't the same world today as it was 10,000 years ago or a million years ago, that this change had gone on. It's not entirely new, but it was the hot thing at the time. So they started asking the question about whether or not the actual nature of the universe changed. Okay, and this is where the American pragmatists, starting with Charles Sanders Peirce, Dewey, a guy named Josiah Royce, a bunch of other guys, got into that. George Hegel was very important, the philosopher, German philosopher. Hegel, Schelling, Immanuel Kant, all these guys are also into this. They see the universe as developing, and I'll come back to that a little bit more. In the modern times, I'm going to mention Dewey and Whitehead, and there's some others that I'll go into as well. And I've already kind of gone through this, what I said, getting ahead of myself. So again, the spectator, the turn that I want you to make is from thinking of the questions that we're asking about the universe as being as if we were spectators. In other words, as if the answers are out there, and they're there, and our investigation of them or our participation in the world doesn't change them, versus a situation in which we are, in fact, active participants in the universe. Now, I'm going to go back. Plato had a dialogue called Timaeus. Anybody read that? Long time ago. It's interesting. And this was the only dialogue of Plato's that was apparently around from 4th century AD to about 1200, when all of Aristotle's and all this stuff came in, because the Arabs had all this stuff, and we had destroyed it in the West, but the Arabs still had all of Aristotle and Plato. So this dialogue, anyway, is Timaeus is this guy, and he's basically asked this question: how did the world come to be as it is? And if you look at it, it's very Pythagorean down line. But what I want to talk about is I'm going to hit on a few things that were crucial, and then I'm going to show that these things that are in the Timaeus also are in the modern theory too, mechanics. So the first thing he says, and this is 6th century BCE, he's talking. The first thing is, he says, whatever account I give you of how the universe came to be, it can only be probable. Okay? Now, one of the ways to think of this is that I think it was the Cock Robin thing. Who killed Cock Robin? Well, are you ever going to know for sure? Because you can't repeat the experiment. Okay, you can't repeat it. So you can get pretty sure, you can kind of track in on it, but you can't. It's a historical event. So if there's any historical events in the universe, it means you can't repeat the experiment perfectly. There's going to be you have to have some probability about how it came about. But that's one sense. I'm going to give you another sense of how it's probable. But he's saying, in an engineering sense, you might say, oh, we built that bridge out there. How did that bridge come to be? Well, I can't give you maybe the details of it, but I can give you pretty probable answers. So that's kind of what he's saying. Okay? So it's not strictly determined. That's one of the key things. Now, he also says that the universe comes to be through the action of the architecton. And this is the world soul, of which we are all parts, I think, as it goes. And the architecton, tecton is really, another word is the demiurge they use. And it comes from demi-ergon. Demi is public, ergon is work, public worker is the engineer. And basically the modern guys at Stanford are translating this as a master craftsman, which is right. And it's sort of the engineer as we think of him today, but it's more than the engineer, I think, because it's not just carrying out a plan that someone gives you as a technician. It's actually coming up with the plan at the same time. So you're sort of the architect and the engineer at the same time. So that's who. So that the universe comes to be through the action of this world soul, this world mind. A key thing is that the plan is. So they say to Timaeus, so what is the nature of the plan from which the architecton works? And he says, well, it's not. Key thing is it's not copyable. I love that expression. It's not copyable. What does that mean? Well, it means it's not a closed system. So, for instance, if the purpose of the universe was to build a bridge, that would be copyable. I would say manufacturable. Okay, could you manufacture this universe again and again and again? Well, you'd have to have a plan, and it would not come about probably. It would have to come about pretty specifically. We want a bridge. We didn't want a dog. So not copyable also has to do with the openness of the plan. Okay, so the plan is not to bring about something specific and closed, and somebody said now that humans on the planet have produced plastic, now we don't need humans anymore. That's what the bacteria just wanted, some plastic. Anyway, the plan is not copyable, so it's an open plan. It doesn't have it's not like I'm an engineer. I'm not a technician. Okay, the architecton is not a technician. Okay, key thing. That was a funny one. Development always moves. He said there's one thing for sure, So one thing for certain, he says, it always moves to the good. And I'm going to come back to that because it's kind of crucial. But roughly speaking, it's because what engineers do is they problem solve. Okay, and what's problem solving? Problem solving is trying to move from a current state of affairs to a more desirable state of affairs, which is trying to work to the good. And you see in Plato and Aristotle all the time, they think all human action seeks the good. And so that we're all, instead if you don't use engineer, you can use the word agent. We're agents in the world. And what are we doing? We're always trying to bring about the good. Even when we do dumb things, we do. We make mistakes all the time. Okay, so the turn that I'm talking about, so there's the Socratic turn where he turns from, well, I'm maybe saying something more about the Socratic turn. Socrates is characterized as being a scientist originally, and then he makes this turn. And Xenophon, who's one of his commentators, actually talks about the day he made the turn. And he talks about turning the soul. And he turns from trying to understand the causal necessity of things, which is kind of what science does, causal necessity, to the question of, they call it management of a farm, or household management, which is how should we live, generally, okay? So there's this sense of going from trying to figure out the necessity of things to saying, wait a minute, that doesn't work. Things don't work that way. So he's saying essentially, we're asking the wrong question. So he says, turning from a spectator thing, trying to figure out how things work, to a participant saying, no, how can we do things in the world, okay? And this household management thing runs through the ancient enlightenment, if you like, of the Athenian philosophies all the way through. This idea of this, all of a sudden, the questions of justice and morality and all these sorts of things come about because they're all questions of how we should live. And I've already kind of said the problem of how we should live and the problem of design. Oh, key thing in this, I think of this as kind of weird. It's sort of like, you ever turn a sock inside out? I've talked about Copernican revolution, but this sort of thing. We're going to move from an answer-oriented framework to a question-oriented framework. Because if this question, the design question is problematic, and it never stops. It's an open question. So it's always like, how can I make the world better? 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 There's not like, oh, it's this way. No, it'll change all the time. I mean, every person's in a different situation, and every era is different. So it's that the participant is basically a question-oriented framework because we're always doing things and bringing out how do we make the world better, but we can only do that by checking it out, by trying to figure out how to make it better. Whereas in the scientific thing, we're trying to like, oh, this is the way the world works, and that's all there is to it. It's an answer-oriented, what's the cause of that, what's the cause of that? All right, so I'll come back to that again, too. So historically, there's classic Laplace's argument that we may regard the present state of the universe as an effect of its past. So Laplace says if I had a supermind and he could see all the particles in the universe and where they were and what they were doing, then he would be able to predict everything forward, and he would be able to retrodict. He'd say everything that had to come. That was so actually strictly determined universe. Okay. I'll read this to you so you don't read it. Isaac Newton says, "It is not to be conceived that the mere mechanical causes could give birth to so many regular motions. The most beautiful systems of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being." Some people think that Newton was the great scientist. He spent most of his life on theology, actually, and he was completely convinced that was the way to go. Anyway, so there was controversy about that in the past. But there was this sense that the universe was deterministic, was this Laplacian, what they call the clockwork universe, that everything worked forward in a actually rigorous way. That's something happened, and a simple way to put it, the guy who really nailed it early was Poincaré, what we call the three-body problem. It turns out in Newtonian mechanics, if you have if you ever work on Newtonian mechanics problems, there's always a symmetry in a thing. You can always, if you want to deal with the Earth, you say, well, you don't deal with the whole Earth, you just sort of assume it's a point with the same mass, and then you can play with it that way. So there's this way of simplifying things in order to do Newtonian mechanical physics. Okay, so even if you have two things, these two things, you can always have a center point with those two things. So you always have a symmetry there. If you have three things, there's a problem, particularly if they're self-gravitating things. And what happens when you have three things and they self-gravitate, there's no symmetry. Okay, the way they behave goes crazy over a period of time. And this, Poincaré pointed this out way back, and then Poincaré finally started taking it more seriously, and if Einstein hadn't been around, you never would have, well, Poincaré wrote his theory of relativity just a little bit before Einstein, and then Einstein's, took off, but it's really basing on this three-body problem. And what it says is actually this idea of a clockwork universe never really worked in the first place. Okay, that the clockwork universe is only going to work if as Laplace said, this state of the universe leads to that state of the universe that I can predict, that I can predict, that I can predict. And what Poincaré says, even if you have as little as three bodies moving around, you can't do that. You're not going to be able to predict. Okay, so.
You're talking about chaos, right?
Chaos theory, yeah. And it came up later, obviously. Poincaré had it early, and it took, as people say, that everybody forgot it for about 80 years. And all of a sudden, chaos theory came back. But he had it back then, and he didn't sort of think it was important, because people were seeing all the successes of the Newtonian theory. You could predict this, and all these wonderful things it was doing. They weren't worrying about where it didn't work. Okay? So then I just got to figure out where it didn't work. So, and then this is part of the then something happened again. So, we all know special relativity, quantum theory, general theory, relativity. And in my Hawking book, if we ever get it out there and you guys read it, the real history, sometimes you hear this history of relativity coming up because the Michelson-Morley experiment, and did we see light, shifting through the ether and so forth. The reality is we had this really isn't what Einstein was thinking. The reality is there were two separate research programs. One was a Newtonian program having to do with particles and things bouncing around and atoms, and they bounce off each other just like billiard balls. We had a billiard ball universe. Then we had this other research program, which is not spoken of so much, or it wasn't for a while, about electromagnetism. Okay, and electromagnetism was all about continuous waves and propagation of signals and all that sort of stuff. And these two programs had different kind of phenomena, and when you try to put these two programs together, they didn't come together too well. And that's sort of the basis of relativity in a way, and quantum theory, this common basis. So we know what happened. One of the things that happened was this uncertainty and indeterminacy. And one way to express it is to say that the quantum mechanics discovered an irreducible probabilistic factor. That's one of the expressions that's used between states. So to go from one state to the next state, it wasn't just a question of this state strictly determines the next state. Okay, there's something wrong with that. So you might say the term that's used sometimes is underdetermined. Okay. It's not that there's no relationship between the current state and the next state. It's just that it doesn't strictly determine the next state. Okay, so I'm going to just jump over that. So this kind of transition. So one of the things that's been questioned that really came up, I'm doing this backwards a little bit, but John Barrow asked the question, what if I reran the history of the universe? Let's go back to the Big Bang, run it forward. What reason do I have to believe that I'm going to get the same universe? And he says, zip. Okay? And he looks specifically at what I call the constants of nature. These are things like the charge on the electron, the mass of the proton, the various things like that. And there's certain ones that, anyway, you can make them without, it's not centimeters and millimeters and seconds, but they're just these constants of nature. And you can read his books, great book. And basically John says, like, if you ran the universe back and forward, you're not going to get that. And this is like 15 years ago, and physicists knew this. It's now become quite the thing. And now you have this idea of multiverses. So the idea is that if I ran the universe back and went forward, well, what are the possible universes that could come out? Huge possibilities, okay? Huge. And how are you going to predict? You can even get universes where matter doesn't form. You don't even get electrons and protons and atoms coming forth. You get this mess. I mean, so how did we get this universe, this particular universe? So I love this expression, and Brian Greene has this expression in his book, Fabric of the Cosmos, where he says, physicists are now appear to be in the worst possible position as regards predictability, prediction, and explanation of the evolution of the cosmos. So if by laboratory physics we go back and say, okay, we know the laboratory physics, start with some initial condition, where does it go? Well, because of the chaos in part, and other reasons perhaps, it could go almost any way. So science was supposed to be like, I can predict, right? So it's going to actually, we're in the worst possible position. We can't predict anything. And it doesn't necessarily have to start at the beginning. You can start 10 billion years. You can start whatever. I mean, figure the universe is, 13, 14 billion years. You can start anywhere along that line. You have the same problem of predicting what's going to happen next. So this is kind of weird. Like, we went from the Laplacian universe to a situation where we're saying we can't predict anything. Okay? Now, what they can't predict is very important. So, and the other guy who, if you saw, what was the program last night? Larry King. Hawking was on Larry King talking about aliens or something. But there's something called the Hawking-Hartle thing. So Hawking goes back. He says at a certain point at the beginning of this Big Bang reasoning, the universe is so small, excuse me, so small that quantum phenomena are operative. So he's sort of saying, he and Jim Hartle sort of say, well, as the universe expands, it's a quantum thing. So it has a certain amount of waves and particles and stuff going out, but it's never going to be predictable. There's always these things. Hartle says, well, there's something you can sort of say some things about the universe in general, but the specific organization of the universe and where this stuff comes out, simply not predictable. So this is not like out there. This is main stuff. Now, the original rerun the tape argument actually comes from Stephen Jay Gould. So I say I'm a little bit backwards historically here. He did it before Barrow did, and Barrow actually specifically makes the analogy. He said this is like what Stephen Jay Gould was asking. And Gould asked the question, what if I ran back biological evolution? Okay, let's go back to, I don't know, what are we, 3.7 billion years on Earth or something. Let's run it back and let's run it forward. Okay, what reason do I have to believe that we'd have, we'd be sitting here in this room with the kind of, 5 fingers and so forth. And Gould says, zip. Okay, he says because of this random mutation thing and the fact that even the niches that the organisms are going into, there's nothing that says there's one niche or they're competing for one thing. One time it's a niche this, one time it's a niche that. I mean, our progeny may end up being mosquitoes or something else. I mean, there's no sense of directionality built into this random mutation and selection thing. Okay, selection is just selection of the day, and random is random of the day. So Gould says you run the thing back over again, you're not going to, there's no reason at all. So does that evolutionary thing explain? 2 things. A, I can't predict. But if I can't predict what's actual, say, okay, how did this world come to be? The answer is I don't have any explanation for it. So again, we're in kind of we're in weird ground here. Now another thing I wanted to just point out, so Darwin is writing at a time when Newtonian theory, probably even with, maybe quantum theory is better now, but certainly over the last couple hundred years, Newtonian theory was the most successful, the best, the most cat's ass theory around. I mean, you could do all this stuff with it we could never do before. Amazing theory, huge success. And all of a sudden, here's Darwin talking about random mutations. Okay, where's random? I mean, there's no random there. I mean, Newtonian thing is this nice clockwork deal, guys. I mean, where's random coming from? So I just wanted to get a sense of that's kind of weird. That he be talking about random mutations in an era that's dominated by this clockwork universe going forward. So in order to figure this out, we're going to do a little slight diversion here. And the diversion is a little brief history of chance. And I was obsessed with this when I first went to grad school. It was like, wait a minute, how did so much chance get into science? And the statistical reasoning and confidence levels and all this gobbledygook, because I was sort of a Karl Popper guy, and it's like, if you do an experiment and it doesn't work, you chuck it. I mean, it's like, don't give me the statistical mumbo jumbo, So I looked at it, it was very funny, and to be quite honest, that was like in when was I obsessed with it? Probably in the late 60s, and I didn't figure it out until about 5 months ago. It turns out, historically, that the observation of chance phenomena, things that were considered chance phenomena, really started in sociology. And there's probably some other people besides Quetelet that were doing it. There's a great book called The Drunkard's Walk, if you want to read. It's a pretty good history of this. So Quetelet and these guys, they were looking at all these statistical patterns. They were looking at all these normal distributions in populations. They were doing, a lot of it had to do with census data. So for instance, the number of suicides in France, okay, that was one of the deals. So they're doing a census. The number of suicides in France was sort of like, there were 18 a year, but it wasn't exactly 18. It was sort of like a statistical distribution around 18. And where they occurred was all geographically distributed too. So they're looking at this and they're going like, why would that be? What kind of a phenomena is that? Because you're seeing it, it's real, it's an ensemble phenomenon. Okay? It's not about the individual things. You can't predict the individual things, but it's sort of like with chaos theory. There's a sort of a determinism in it, but it's a kind of a different kind of determinism. It's something different going on. So the reality is, and Mlodinow argues this anyway, that it really starts in the sociology, okay, and only later gets into he says Maxwell read it. He says James Clerk Maxwell, electromagnetic theory and thermodynamics, picked it up from Quetelet in a book by a guy named Buckle, and and it gets into quantum theory too. But it's sort of weird that it actually started on the macro level and went into the micro level, because now one of the arguments in quantum theory is that the statistical stuff only happens on the micro level, and as you go up to the macro level, it disappears. It's not true. So the other interesting thing is that where did Darwin get this idea that there were variations in populations? Well, it came from this guy, Francis Galton, who happened to be Darwin's cousin. And he was like Quetelet, and they started going like, oh my God, look at the height of all the people. There's distribution, and they're looking, I mean, everything, your fingers, toes, everything. They were looking at the populations and trees and the distribution of things. They're just finding normal distributions everywhere, just all over the place. This is crazy. So Galton really brings the observation of statistical chance phenomena, variations, into biology. It comes through him. He's obsessed with it, and he pulls it. And that's where Darwin got it. Now there's another guy I'll just mention. This is Brown, a Brownian motion. And Brownian motion, if you don't know, is like if you put a little dust speck or something in some water, the typical thing, and you look at it with a microscope, it does this random walk thing. And that moves around. The question was, why is that happening? And the reasoning ultimately was that it was occurring because all the molecules down on the level, there were these atoms down there, and they're all bouncing around, and they're bouncing around in a kind of random way, okay, which is fundamental to why, I mean, Einstein cites Brownian motion very fundamentally in a lot of his reasoning about quantum theory and so forth. So Brown was another one, but he's starting to see it down, not at the quantum level. He's seeing this is particles that you can actually see under a normal microscope. So anyway, and it's seen, basically the idea is that there are these thermal fluctuations. If you heat up the water, they move around a little bit faster, and you slow it down. You know, so there's thermal. Yes, yes. And he saw the atoms in there, although atoms is already there. But this is kind of an interesting one. So this, I just came across, I just Googled this a couple of days ago. Turns out this is Lucretius, who was one of the guys that atomists way back in the ancient period. And he says, observe what happens when sunbeams are admitted into a building and shed light on its shadowy places. You will see a multitude of tiny particles mingling in a multitude of ways. Their dancing is an actual indication of the underlying movement of matter that are hidden from our sight. And basically he actually argues that he's seen it with dust particles. So it's just like dust particles are essentially suspended in the air, and they're doing the same thing. The air molecules are bumping them around. He's seeing these things go around. And it's exactly the same observation. I hadn't seen that before. Interesting. So the Greeks weren't all that crazy. Huh? So here's the thing. So what did Darwin mean by random chance variation? Because they asked him, and he said, I don't mean chance, like it's going to violate Newton's laws, and say, well, what do you mean? And one argument was like, well, it's just kind of complex, and so it kind of looks like it's chance, but it isn't really chance. But that isn't really what he had to say. And I have this allegory, I call it allegory of the eagle, to give you a sense of what it is. So God creates the universe, evolution is going on, but it's very slow, and God's getting bored. So God figures, like, if I could just watch the eagles soar, I could put up with the timeline here. But there's no eagles yet. So he's finally got to the point, evolution's finally got to the point where he's rudimentary birds. So he figures like he's going to pull a little trick here. So he creates a wormhole, and he brings an engineer back from 1850s. This is before airplanes, but close, okay? Maybe 1875. Brings this guy back, and he says, here's the deal. I want you to work on this rudimentary bird, and we're going to accelerate evolution. We're going to cheat a little. We're going to accelerate evolution, and so that I can get to the eagles, and I'm going to be cool, and I'll send you back. You'll never remember anything. So, not why God couldn't do it himself is a question, but so I want to ask, what's the slowest way that this engineer could possibly work? Random mutation. Okay. Slowest way he could possibly work is random mutation. So what Darwin is saying really when he says that mutations are random, he's saying they're not intelligent. They're not intelligent. So if you consider it in a general environment, so if an organism's in a particular niche and it's having some mutations, are those mutations coming forth to solve a problem? Or are they just random and they may or may not solve a problem? You may never get the right one or anything. In other words, is there any intelligence in the mutations? Okay. And what Darwin is saying is no, there is no intelligence in the mutations at all. And that's what you mean by random. It means doesn't make any sense. In other words, whatever these mutations are that are coming up have no relationships whatever to the awareness of the organism of its environment. Okay, so if I'm an engineer and I'm getting cold, I might shut the door or something. You know, like, well, that can't have, that's a mutation. Okay, so you get the idea that random means non-intelligent. Okay, so we'll come back to that a little bit. The other factor here that I'm going to go through real quick in quantum theory. So quantum theory comes up and it says, this, in a sense, that there are no universal laws. That if you look at the universe one way, you see one type of law, and if you look at it another way, you see another type of law. Okay? There's two different laws. This is like saying there are two different realities, two different objectivities. Well, that's an oxymoron. Objectivity is supposed to be the way the world is. So all of a sudden, what we found in quantum theory was, in fact, that there wasn't a universal laws. Now the question is, people would question this, but this was the fundamental finding that there, and this really goes back to these two research programs I talked about, the Newtonian program and Maxwell's electromagnetism. That these two programs don't mesh. Now the interesting thing that starts coming out is you see these programs are somehow like left hand, right hand to each other. Okay, that there's something about these two different research programs. I look at the world that way, I see this. I look at the world that way, I see that. And as de Broglie said, actually, if you look at things, real things in the world, not these extreme atoms or not these extreme waves, everything seems to have kind of an atomistic character to it and a wave characteristic to it. Okay, this is de Broglie's thing. So everything is sort of, so is the electron a particle or a wave? Well, it's both, but it's neither one universally. Okay, so it has if you look at it one way, it shows particle behavior. If you look at it another way, it shows wave behavior. So what is it? Is a particle or wave? Well, particle and wave are defined as like local and non-local. That's another way to put it. So particles are localized in space and time, and waves are non-localized in space and time. So is it local or is it non-local? Well, you can't have it local and non-local at the same time. Okay, so this is a paradox. I like Feynman. You know, if you think you understand quantum theory, you simply haven't studied it long enough. So, but anyway, so this is the thing. We see two different causalities: this sort of clockwork causality and this sort of cloud-like causality. Thus, the title of my book, with Hawking, of Clouds and Clocks. So, now the two things that happen in quantum theory, because of this, if I look at the universe this way, I see this kind of thing, and I look at the universe that way, I see that kind of thing. And they're never perfect. Like I say, everything's really in between. It's got a little bit of stuff, but and emphasis-wise, if I look at an electron, I can tell you pretty much where that electron is if I want to look at it that way. If I go the wave way, it goes the other way. So, one of the things that, as an observer now, as an investigator in the world, I'm faced with a problem. The problem is, should I look at it that way or should I look at it that way? Okay, this is an inherent problem. This is a problem at the depth of the nature of the universe. Okay, because of this complementarity, it means that as an observer, as an investigator, I'm constantly, every day, every moment, every second, every instant of my life, I have to make this choice to deal with the universe this way or that way. And of course, it's really this whole range of ways. But there isn't one way. There isn't one right way. Okay, so I have this choice. So choice is an implication. Now, some people have said, because of this probabilistic thing, well, quantum theory says that, you know, some of the things you do are you know, chance governed or something like that. It really misleads, because it's trying to say, you know, I'm going along, everything I do is law governed, and all of a sudden, you know, like some chance thing happens. It's really about this complementarity of two different orders, and I'm faced with choice. Okay, the second thing in quantum theory is that because of this observer thing, when I look at if I have a sort of abstract quantum possibility here, when I look at it, I change it. Okay, it's fundamental to the quantum theory. So when I look at it, I change it. I can't go back and look at it a different way. There's no going back. Okay, the act of observation is a historical phenomena. Okay, if something happens. So anytime I look at the universe goes that way. And people say, well, we're creating the universe or something. And that's no exaggeration, but clearly the way in which observers, and of course I don't know whether it's probably you're the one that are driving the universe. I mean, it gets confusing because there are all these observers around, but somehow observation is not relating to one way of looking at the world or one thing in the world. It has this option. So anyway, when I look at the universe, I change it. I look at it again. It's the universe after I looked at it. It's not the universe before I looked at it. Remember, in the spectator thing, the universe is fixed. So I could look at it and then I come back and I could look at it again. It's going to be the same universe every time I look at it. Okay? No longer in quantum theory, every time I look at the universe, I change it a little bit. Okay? And there's a lot of people looking at the universe, so the universe is going. Now, one of the guys, so you think I'm totally crazy, this is a guy named John Archibald Wheeler. When Einstein died, they said, who's going to wear the mantle of Einstein? And everybody said, oh, well, Wheeler. And Wheeler says, I'm not going to do it. Forget it. I'm not going to be the Stephen Hawking of whatever. So two of his students, Richard Feynman and Kip Thorne, just to give you a sense of who this guy was. This is the guy, he also coined the term black holes. Okay, so Wheeler is one of those people who came out and said, actually, what I'm saying about quantum theory, that the world is, part of saying the way quantum theory sets up, that nothing actually happens unless you have an observer. You have to have an observation. That's which is an interaction now. So in order to have an actual universe, you have to have an observer. And then he goes in and says, only universes with observers become real. Okay, so if this is a real universe, it has to have observers in it. That's a very major implication of quantum theory. So, I mean, if you just had atoms popping around, inanimate atoms popping around, that's one thing. But if you have to have observers that learn, different world. So another guy who is a friend of mine who did some work on this early on, Fritjof Capra. And Capra kind of had this, he follows Bohr in this idea of complementarity, and he says what's called Copenhagen interpretation. So he very much gets into this Eastern side. And he sort of says, well, the Eastern mystics, they had the truth in Western science, mumbling on, has just finally figured out that in fact the world has these complementary forces in it and so forth. Fritjof morphs into systems theory, holistic web of life, which is a sort of an ecosystem perspective. He was big. He tells a story that he was meditating. He had a friend of his down in Big Sur, and he's meditating, looking at the sunset over the Pacific, Big Sur, and he has this image of these cosmic rays coming in, and as they hit the atmosphere and hit things, they're destroyed. They destroy things, and destruction, creation, destruction, creation, destruction, creation. So he sees this thing, this creation destruction thing, that the world is in a certain way, and then we destroy it and create a new world, and destroy it and create a new world. So, he gets big into Shiva, who is, in at least one interpretation of Hindu stuff, is the goddess of creation destruction. So he talks about this specifically in his book. If you haven't seen this movie, it's a really great movie called Mind Walk that he and his brother did. His brother was in Hollywood or something. And one of the things that comes out of Capra's book, he told me this, and it's there in the movie, but the significance of it I missed it. At the very end of the movie, he gives this whole ecological systems thing, and like, here it is in the world and a little bit, and we're all part of this whole thing. And then Sonia, who's I can't remember her name now, actress, but she's his persona in the movie. And then at the very end, because I go, where are the people in your system, Sonia? Because the question is, where, as Capra goes, he has all this complementarity, he has all these things going, but he's still kind of like a physicist, and he doesn't have any people in the world. He has organic things, but are there any people? Now, I say his book, The Turning Point, sort of it, and that's exactly what he's doing. But what he's doing is kind of turning from one to another, whereas I want to be in the middle, but nonetheless. So just to think, again, I'm not making this up. This is the coat of arms of Niels Bohr, who did the Copenhagen interpretation of quantum mechanics, okay? And you'll notice, I don't know if you can see it very clear in here, this is the yin-yang diagram in here. And across the top here, it says, contraries are complementary, okay? And the idea, one of the fundamental principles of quantum theory, as Bohr put it, is that these are unresolvably different, okay? They're just, there's no common denominator. This is a very fundamental deal, okay? So I'm going to go to the historical thing now. So if the universe is historical, how do you describe a historical universe? If I want to describe a universe as mechanical, I can kind of do it, but if it's historical, how do you describe something that has a history? Okay, it's a different kind of problem. Okay? So, in fact, Newton was all over this, and Newton sort of thought that, mechanics and the physics, that was sort of trivial. The big question was the story of the universe. He wanted to know the story of the universe. And he spent a huge amount of his time, and for him, of course, the best game in town for the story of the universe was the biblical story. And so he wrote a ton on that. This was ignored for years, and then maybe in the 60s it came out again. So a story is a narrative. A narrative has certain requirements to have a narrative. One is that you have to have a problem. So if you're writing a book, some of you write novels or something, how do you have a novel? You have to You have to have a narrative. You have to have a problem. You have to have people who struggle with that problem, with the obstacles that there, and then they overcome. So those are kind of like, if you're going to give a description of the universe, what's the history of the universe? Well, it has to have these characteristics, as you'll see. I want to go back to what did Darwin mean by this? A key thing in the complementarity is that, and because these are unresolvable, that's another way of saying that these two sides of the universe, or two orders of the universe. If I'm in one order and I assume that that order is real, like particles, then the wave stuff doesn't make any sense. I can't make sense of the wave stuff because I have a certain way of making sense of the universe, and the other way of looking at the universe doesn't make sense. But if I go over to this one and I say, well, this is the way the universe is, and then I try and look at the universe, these other phenomena, they don't make sense. Now, this is quite analogous to politics. Okay, if you guys been following, if you've been awake for the last couple of years, the left and right talk past each other. Okay, it's very, very similar. And I think that I would argue in a broader thing that the left and right politically are complementary in the same sense that wave and particle are complementary. And the key is that, you ever hear the expression where you go like, if I were you, I wouldn't do that. That sort of thing, whatever it is you're about to do doesn't make sense in my terms. In my way of looking at the universe, we've had this thing, you're going to marry that guy, or you're going to go off to, boy, I wouldn't do that if I were you. That's another way of saying what you're about to do doesn't make sense in my terms. Like if I look, the way I look at the world, if I were you, that wouldn't make sense. Now the key thing is if I say law-like, say the world's law-like, then what would the opposite be? Not make sense. It's chance. Okay? Well, chaos, but real chance. Chaos is a little bit more structured, but chance is like nothing. Okay? Chaos is underdetermined. Chance is like... So what I want to say is that these two sides, what's looked at as a chance thing is really just these two things looking at each other different ways. And what we want to do is we want to find a world in which we can see both of them. Okay, we want both these. Now this is what Bohr did. Okay, Bohr says, complementarity, he says, I want both these babies in there. Einstein goes, no, you can't have both of them because they don't make sense in terms of each other. Bohr says, no, you can't just say it's all going to be particles and we'll pretend like the waves are some sort of secondary phenomena. You can't say the universe is all wave-like and particle phenomena. But you got to have both of them. It's kind of a paradoxical situation, but he wants to, that's what complementarity is about. So, to give you a sense there, I want to move on here quick. So, this guy, Unger, who's sort of saying the same thing. I'm going to go on quick. So, I'm going to have to move forward here quick. Not essential stuff, which I've already said. So I want to go to the second turn, the pragmatic turn. So if I'm choosing, in philosophy of science, one of the things we do, which way, what are you going to believe about the universe? Well, if you have this complementary thing, complementary is a range of things. Okay, it just says there's this one extreme and this extreme. There's a whole bunch of stuff in between. What are you going to believe? What's going to be the basis of believing? And the argument was that the evidence, give me all the evidence you want, it's going to underdetermine my belief. So, and there's another saying, I'm making choice. I'm choosing what I believe in some sense. Okay, in a particular time, I'm going to choose what I believe. Now, the guy who Kuhn pushed this particular, and the main thing that to understand in this is that the choice is essential. Okay, it's not like, in other words, that the world is not one way as part of this thing. So it's undermining that idea of objectivity. I'm going to stiff on here. So I have, again, that same thing, the pragmatist move from this thing of how does the world work to how should we live is the big turn. The other thing, just very briefly, one of the things that happens in here is that what was random mutation for Darwin is this guy, a friend of mine, Robert Reed, is emeritus up at University of Victoria. This is evolution by natural experimentation. So what Reed says is, wait a minute, these mutations aren't random. I mean, if you're really looking at the data, they're not random. I mean, there's like 10,000 base pairs, 100,000 base pairs, a million base pairs. They're not picking them out randomly one by one. Okay, we used to do a deal in high school, actually. You radiate fruit flies and stuff like that, and you go like, well, hey, see, chance, there's this random mutation. Well, yeah, but you run the experiment again and again and again, and you get the same ones. Okay, in other words, so there's a bell curve. There's definitely a bell curve of the mutations you get, but it's not every possible mutation. I mean, that'd be stupid. I mean, it's like life isn't that dumb. So all of a sudden what Reed's saying is that like part of what's going to a random mutation, part of the reason for variation in populations, they're sort of like natural experiments. Okay, they're kind of putting out feelers for some reason, all right? Okay, choice is freedom. So push the key terms here. So quantum mechanics says I have some sort of freedom in some sense. I mean, I'm not clear. We're struggling to try and figure out how to make sense of that freedom, but I'm free. But freedom is also a problem. It's like I got to choose. I'm free. What am I going to do? You know, it's like existentialists say this. You know, like here I am in the world, and I have all the ability to act in the world, but I have no script. You say, well, what do I do? Well, you better, you know, do a two-step. Figure out what you're going to do. So you're constantly making these choices. But choice is a problem. I mean, I don't know how to choose. I don't know what I should do. You know, what should I do? So how should I live? Okay, real quick on Royce. I'm going to jump forward. This is one of the American pragmatists. And Royce says, basically, he says, any theory of the universe that you come up with, this is a big metaphysical argument, any theory of the universe you come up with has to account for itself, has to account for you having come up with it. Okay? Pretty straightforward? So, in other words, you might say, are there any physicists in the physicist world? This is Capra's problem of showing you where are the people in your world. You got to have people in your world. Whatever your theory is has to have people in it who learned the theory. Okay, and if your theory is not consistent with that, then it's not an acceptable option. Okay, it's not self-referentially consistent. So, one of the implications of this is what Royce pushes for. He said problems have to be part of the world. That was what he calls the problem of problems. He said whatever theory you have has to be able to make sense of the existence of problems in the world. Okay, and in mechanics, of course, there aren't any problems in the world. I mean, there's just stuff happens. You know, there's no real problems. So anyway, so that's a kind of a good criteria, and the implication again is just another way of arguing that this problem solving or this action, this freedom, this choice is actually part of the world. And any theory you have that doesn't have that in it isn't self-referentially consistent. One way to push this a little further is to say, if I'm a scientist, do I have the freedom to check my experiment? I mean, if everything I'm doing is determined, you know, like I'm determined to learn that, 1 over r squared or something, am I determined to do it? Well, how would I check that? I have to be able to design it. I have to have a certain amount of freedom to problem solve to actually learn in the first place. Okay, here's that real quick. Again, I'm running long. So Karl Popper, who's kind of one of my guys, Popper basically argues that when you learn, it's a qualitative change. So if I actually learn something, the theory that I am now adopting has to be different in some way than the earlier theory. We just say if it's just a logical implication, if I could deduce this later theory from the earlier theory, I didn't really learn anything. I mean, I'm just like, it's an implication, okay? So if I actually learn something, I'm making a qualitative change. And one of the terms is incommensurable. It's just a big word for different, qualitatively different. It just means that when I learn something, it's not just systematically reasoned, okay? There's a better understanding that occurs in the later theory than the earlier theory. This is like the whole of 20th century philosophy of science in a nutshell. Okay, real quick summary. So spectator, mechanical, it's a closed system, it's an answer mode, and I want you to move to participant, where a choice is agent freedom, and it's a question mode. And the question mode just means it's open, so we're building the universe as we go. Might have to run quick here. In the pragmatist model, what we learn is actually if it doesn't have any cash value, it's a nice, wonderful American crass term, if it doesn't have any cash value, then it's not real knowledge. So if there were universal laws, you couldn't do anything about it. Okay, the universe is going to do what it's going to do, and that's it. But if you have this kind of weird situation where whatever it is we mean by knowledge empowers us to actually solve problems, to change the world, to redesign, to reconstruct the world, and that's, okay, so that's the change in the idea of knowledge. So the architect on being an engineer is problem solving. As a problem solver, he's trying to make the world better, and that connects with Dewey's basic deal, which is that what we're doing as participants are constructing the good, or something like that. Real quick, engineering, if you look at Herb Simon, he was actually an economist, got the Nobel Prize, wrote a really nice book called Sciences of the Artificial. And first of all, the field of engineering, one of the things I'm going to go is engineers are participants, scientists are like spectators, okay? So as an engineer, so engineering, if you look at an engineering textbook, it's defined by the problem of design. Okay, so engineers are all about changing the design, designing things, okay? Scientists are about discovery of what's fixed, okay? So engineering. So what is problem solving? It's moving from one situation to a better situation, which is trying to make the world better. Vincente, another guy in this field, sort of says, engineering isn't applied science. Science is engineering research. So what the scientists are really doing is discovering these relationships, these regularities, but only the only ones they can discover that they can actually learn are ones that are useful, okay, which have cash value. I'm going to jump past this because I want to get into this. Okay, so a key question in this. Okay, so Bristol, the universe is developing. I mean, what direction? Where's it going? And what? You know, the good. I mean, good. Yeah. So what is that going to do? So the question is, what is the problem? And what I want to focus on here is the definition of better. So one of the things is that better is somehow tied to freedom. So if I'm getting more freedom, the world's getting better. Okay, it's an increased ability to do things in the world, to do good things in the world. So I'm always trying to do good things. So if I get more ability to do good things, then that's better. So Hegel's way of saying this was that, I mean, he's pretty deep stuff, but he basically says what history is the unfolding, the manifesting of an idea or a concept. And that idea is freedom. So history is this coming forth of freedom. So the parameter, so to speak, of history and of evolution in some sense is freedom. Okay, well, what freedom is the ability to act. Ability to act is the ability to bring good things into the world. Okay. All right, so let's look at what does better mean in biology. So Lovelock is asked by NASA. He says, look at Venus, look at Mars, look at Earth. Tell me which one's alive. Venus and Mars are totally dead. Everything you can see in the spectrum of their atmospheres is completely consistent with a complete equilibrium system. Every chemical reaction that you would expect to go on has gone on. They're just. But if you look at the Earth, we have this non-equilibrium atmosphere. It's all this oxygen is very reactive. Oxygen all over the place. Highly reactive atmosphere. We have a non-equilibrium atmosphere. Good evidence now we've had it for at least 3 billion years, if not more. It's kind of weird. So one of the things that Lovelock does, he said, let's look at Earth 3.7 billion years ago. Give it a little life here. And history of the whole system. Let's not worry about origin of species. Let's look at the history of the whole system, the whole ecosystem, biosphere, evolution. He says, what's happened there? He said it's an increase in the amount of stuff. I'm going to put this in there. I'm going to jump ahead. But he's the increase in the amount of life, the increase in the diversity of life, and the number of ways of making a living. Okay, that's easy. But there's something else that's increased too. And what others increase is the efficiency of the overall system. It's a kind of thermodynamic idea. But it says essentially that the engine of the Earth has got better and better. Okay, you can have more, you can have more types, but it's got better in a different way. Okay, it's got better at, these are the guys here, it's Dorian Sagan, who's Carl's son, and Lynn Margulis's son too. And basically, you have more, but you also have a more efficient design. So it's sort of saying if I have a better engine, then I can, their expression is degrade the gradient. There's this gradient, so in order to have something go on in thermodynamics, you have the sun out here, that's your heat source, and you have cold space, that's your heat sink. You got to have a source and you got to have a sink. And then we're the little engine in between. Okay, that engine is not just more and more diverse, it's actually more efficient. Okay, so there's something different. I'm going to go on with it. So it's better, it's more efficient, there's something going on here. So I'm going to wrap this here because I don't want to get into Romer here. So roughly the argument is that the evolution of life on Earth it's increased its capacity to perform work. Its capacity to perform work is kind of like the technical thing. So the increased capacity to perform work, the argument here is that that's the parameter of evolution. Okay, so what's increased in evolution over time is the capacity to perform work. Okay, what is the capacity to perform work? Freedom? Ability to act? So we're getting tight there, all right? So, and I would say that's a parameter, that's a betterness. So If you talk to the neo-Darwinians, you talk to Sean Carroll, who will be in here a while, Sean says evolution is just change. This is consequence of Steve Gould's argument. So you guys have no reason to say that evolution is going in any direction at all. And they're going like, you're right. It's random mutation. There's no reason to pick one niche over the other, so evolution is just change. A lot of people haven't figured out that this is what the neo-Darwinians are saying. They don't have any theory of evolution as we would normally understand it. Because everybody's like, well, what's the parameter of evolution? If you're saying it's going somewhere, if there's a progress, what's the progression? Well, it hasn't been around. So I'm saying this is the answer, is this increased ability to perform work. So I'm just going to go for it. So this is a key thing. I want to look at economic betterness now. Okay, so we already got a sense of biological betterness. It's this thermodynamic, increased capacity to perform work, a better designed machine. So the life has got better, but it's also got more efficient, more sophisticated design. Okay, so in economics, in old economics, scientific economics was essentially equilibrium economics. You got supply and demand, production, consumption, come to equilibriums. Sometimes things get knocked out of balance a little bit, but they're always going to come back to that. And this is very nice. It's a sort of a, you had people who are rational optimizers, which is sort of like stupid, but they did it anyway. And the reason you have to do that because you can't make generalizations unless everybody kind of has the same knowledge and so forth. Anyway, supply demand models, very very mechanical, very quantitative. Okay, that's why the economics departments are in there. They all want to be able to measure stuff, make mathematical models of it, and so forth. So, but what was better in scientific economics? Let's see, I'm going to go real quick here. So better was more, and it was more diverse. We talk about value of specialization, although I don't think there's any explanation of why specialization was better. But the main thing was it was quantifiable. And interactions are always zero-sum. So the perfect equilibrium is when the amount of things are produced and the amount of things are consumed are exactly the same. That's the equilibrium state. That's perfect. Whatever we're producing, there's no excess of this. There's no scarcity of that. Mainly you take your fair share. Okay, so, and this is Samuelson economics. So in order to make the economy better in a quantitative sense, you just add quantity. It's like another McDonald's and another McDonald's, another McDonald's. Okay, it's quantitative. There's no sense of qualitative improvement. So just more. And they would say that, idea of qualitative is a philosophical and you can't decide it empirically. So, you're scientists. Stop talking about things. So again, then something happened. So roughly speaking, it starts with Sumpeter and Solow in the 50s. They're looking at what's happened since 1850, Industrial Revolution. They go, my God, there's been this incredible improvement in lifestyle in the industrialized countries. There's this huge increase in productivity. So the amount of output per worker has just gone up. And they go back and say, this is because of technological innovations. Okay. So technological innovations are qualitative changes in the structure of the economy. Okay, an innovation is not a logical extension of anything, right? It's an invention. It's creative problem solving, and because they're creative, they're not either predictable or once they're here, you say, how did this come about? Well, you can't say. You can give a story, a probable, but it doesn't come out. So. All right, so increased productivity, which is output per worker. So how much each of us is able to produce in our economy per worker has gone up enormously. And a bunch of figures, but roughly this was, the output per worker in 5,000, and you can see boom, boom, boom. And it really takes off right in here. So, a worker in 5,000 BC was producing in today's terms like $130 worth, per annum. And now we're doing this. So something big has happened there, okay? And what? Per year, yeah, per year. And this is one of the examples that that Romer, who I'm going to tell you about here in a second, talks about. Just to give you an example of how technology, this is like the amount of BTUs to produce a certain number of lumens, but or how many lumens are produced by one BTU. Another way of casting this is how Romer had is how many hours do you have to work to produce a certain amount of light. Okay, deal. Romer starts off his talk with these kids in Nigeria, sitting under they're in the parking lot of the airport, where that's the only place there's light, so they can read. He said this is dumb. Point is that this is an example of productivity gain due to technological innovations. Okay, we can produce light now much more efficiently for much less per hour of work than we ever could before. So before Romer, because of this equilibrium always, economists saw that the economy would jump up and down. It would, they would find different equilibrium points. Someday be a war, economy would go down, or maybe we won the war, our economy would go up. But always going to the equilibrium point, or supply and demand, stuff like that. So these things that bumped it up or down, changed the equilibrium point, were considered to be external to normal economic activity. We're just producing, we're trading, we're doing all that. So whatever is bumping it up and down is something external to normal activity. Okay, that's the key thing. So, okay, and the term used was exogenous. Just means coming from the outside. So the causes of these changes in the structure of the economy were exogenous. So then, So then Romer writes this famous paper, you've all read it, of course, called Endogenous Technological Change. You can actually get it on the internet. Go to his website at Stanford. So what he changes the definition of economic activity. This is the paradigm. This is the turn. Okay? He changes the definition of economic activity. He says what we're doing in an economy is not coming to equilibriums. I mean, you could do that. You can look at it that way. Fine. No, what we're doing is we're always trying to innovate. We're always trying to produce something good in the world. Every one of us is doing as an actor. We're all kind of agent engineers. We're all so normal economic activity now is problem solving. Is trying to bring something good into the world. Okay, that's the base idea. So Romer's turn, his paradigm shift, is that normal economic activity is problem solving. Economic problem solving is open-ended. Is like the construction of the good. Now Romer, this open-endedness is important. Increases productivity. What's productivity? Productivity, of course, is just the capacity to perform work. Surprise. So you see the analogy here between what I argued in biology is increasing capacity to perform work. What's going on in economy? They just mesh perfectly. So evolution, in a sense, one would start thinking is an economic activity in this sense as well. Construction of the good. Now, give me 2 minutes here. I'll finish this off. So what he's doing is changing he's changing our understanding of what we've been doing. So we were just supply demand and we were rational optimizers. No, that isn't what you were doing. You were actually trying to make things better in the world. We're trying to create real value in the world, the construction of the good. So Romer's also called a post-scarcity economist. Okay, this is fun. So in classical economics, it's scarcity is big, and in fact, up into the 1950s, and even in some colleges, you still get it. That economics is all about scarcity. There's a certain amount of land in the world, there's a certain amount of water, there's a certain amount of gold, and whatever it is. And more people. So, like it's the smaller amount, the same amount of stuff, more people, it's scarcity. And so we're all competing for these goods, and it's a big, free-for-all. Everybody's competing with everybody else, and some survive and get to push their genes on, and all that sort of bullshit. So and that's what it is. So what did Romer do? So Romer goes. There are material resources like land, and the planet's only the biggest planet. And then he says, but he calls them recipes. And recipes are what engineers come up with. Recipes about how to develop those resources can be shared without diminishing. Okay, so all the technologies, all the knowledge that I have of how to do things, I can share that. It doesn't diminish it. Okay, it doesn't diminish. In fact, I want to share it. I mean, give it out there so you guys can solve problems too. So knowledge of how to do things is something that's shareable. There's some technical terms he uses about expropriatable or something like that. But so what is it? These are how to live. This is knowledge, again, recipes are how to live. So this gets better. So Romer, some recipes are better than others. Some engines, I got a better engine, I got a better computer, so forth. Better recipes increase productivity. And every time we get a new recipe, a new technology, you can think of it in terms of hardware terms or software terms, it metamorphizes the economy. We reorganize the economy as we do this. And those reorganizations, so new recipes continually reorganize the economy. New, better recipes, innovations. Now here's the big thing. They're also synergistic. Here's fun. So Romer has one example where he says, he said, I used to pay $100 for a gigabyte of RAM, 10 years ago. And he said, now I can get 10 gigabytes of RAM for that. He said, and I didn't do anything. Think about that. So what happens when that RAM goes from $100 down to $10 or 10 times? everybody in the economy that can buy RAM now is all of a sudden in a position to be more efficient, okay, to do more. Okay, they've been empowered, their productivity, potential productivity is increased. So every time somebody out there, one of you brilliant people, invents something that makes it so that I can buy a product for less, or something that allows me to do something more, that's my productivity just increased, at least potentially. So I retire. So, and the synergistic argument is that these technological innovations that we use to restructure the economy actually exponentially increase the capacity to perform work. They're not just additive. Okay, so some people said, well, the productivity increase has been 2% since 1850 or something. I got to calculate it. Another I say, no, it's more than 2% because there's this exponential effect on all the other ways of doing things. So each individual, it increases for individuals and for the whole. So what happens is that economies produce natural overabundance. It's not a scarcity issue. In fact, what we're producing is we're so good, we're producing more than we can use. We have so much potential here. How many people here think they're underemployed? Yeah, probably everybody. I mean, everybody I know thinks they're underemployed. Okay, this is precisely the opposite of the Malthusian argument. Okay, in that scientific zero-sum game thing, the economy, there's this limited resources, and we're all competing for this. And this is the metaphor that defines pretty much Darwinism going on. This is a big, big change, folks. So these changes in productivity that we've seen since 1850, this is what stimulated it. But all of a sudden, we're seeing that economies, technology is huge in the economy. And when you put these technologies in there, we're just going crazy in terms of productivity output. The wealth, the lives that we all lead. I mean, go back to 1850 and think of how people were living back then and where we're living now. It's huge increases. And what Romer says is that there's no, these are productivity gains are both a lifestyle, and you can expand this a little bit. But here's the big deal. He says, these changes, as we're reorganizing ourselves according to these new recipes of how to live and how to do things, he said they're unlimited. There's no reason to believe that productivity gains are. He said, we're down there changing molecule to molecule now in the chips. We're reorganizing the world. We're reorganizing, redesigning the world. Those changes are unlimited. They're open-ended, and that's exactly what the architecton was saying. Okay? So the good is really better. It's an unlimited better. We're constantly getting better and better and better. And that betterness, one way of measuring that betterness is freedom, it's capacity to perform work. That means work, not in the physics sense, but in the engineer's sense. The engineer's sense of work is the ability to problem solve. Okay? So as it gives me this computer, I can problem solve better now that I got a better computer, and you go on. Okay? So that's, I'm going to wrap it out here. So that's the abundance argument. Just to piss off the atheists, I sometimes call this the lilies of the field argument. Remember that from the Bible? And Jesus comes up and says, why are you working? Oh, we got to work. He said, don't you think you're provided for? So the abundance argument here is that this is another thing. Oh, this is the last point then. So all these gains, all these recipes in transportation, agriculture. I mean, in 1850 we were producing, corn farmers producing 4 bushels per acre. Now doing 450 bushels per acre per farmer. Now he's got other inputs, of course, but that's huge. Agriculture, manufacturing, health, communication, education. These are not adaptations to a fixed niche, as the Darwinians would have it. Okay, these are not adaptations. These are explosions of qualitative emergence. The world's getting better and better. It's getting more and more powerful. It's expanding. Now, if you take this back to the architecton, the Greeks had this idea. The world doesn't start as a big bang where you have all this energy that then dissipates. It actually goes the other way. It starts as what they call the golden pearl. Okay, which is like maybe it has a yin-yang diagram on it, and it has a world soul, and then it builds and it's constructed itself out, and the energy is expanding out. Now, taking this into cosmology is a whole other game, but well, I'm going to say one last thing, which I said about the computer thing. There's a morality in this, okay? That's very interesting. Turns out that the moral system, the best moral system, as I would imagine it, and the best economic system actually turn out to be the same thing, which is exactly opposite of what the Darwinians are saying, or if the socialists on the other side. And this is because this includes competition and cooperation together in a different sense. So we're all competing for prizes to make the best contribution to society. But the key thing is, it's in my interests that you succeed. That's not the case in a balls to the wall competitive system. In a completely competitive system, the only reason I'm going to cooperate with you is so I can stab you in the back later, so that my genes will go on and yours won't. This is garbage. In this system, this post-Malthusian, post-Darwinian system, there's a morality to it that says, hey, I want you to succeed. What can I do to help you? How can I encourage you? And of course we're doing it. We invest in innovation all over the place. This is the lilies of the field I'm getting behind here. So Hesiod says that before. The last thing really is, I'm just going to end with this, is this final thing, going back to participatory cosmological universe, because all this stuff says essentially, I've pretty good case I've given you in economics, I think. Also a little bit in biology. And I want to say, once you drink the Kool-Aid, once you drink the Kool-Aid of the thermodynamics, of the increased capacity to perform work, which is the definition, I think I actually have it, it's the definition of energy, is the capacity to perform work, that you have to go the cosmology route too. So this goes, certainly economics, very plausibly it's going on in biology, and in fact the whole structure of the cosmos is in fact also going to be something that's increased capacity to perform work. So what's the possibility for? Anyway, enough. Sorry I ran over a little bit there. Questions? This is all so clear. Anybody? Okay, thanks. Yeah, thank you. Does anybody have a quick question, because we're probably running into somebody else's time here?
Thank you.
Yeah.
You gave me a lot to think about.
There you go. And I'd be happy to, if anyone wants to talk to me later, because do you have a question? Yeah, go ahead.
Example, I was just kind of 25 years ago or so, I was data communications, and we got a new Japanese engineer came in. The Japanese are very protective of their knowledge if they give that away. I was teaching him everything I knew, and he was so appreciative, and he's bringing me tea and sake and all kinds of things. But
I think there's this. To give you a sense of this, there's been so much talk about God. We're worried about all these Chinese engineers are coming along, these Indian engineers, and it's like, go baby, think of all the things they're gonna create that are gonna be wonderful new ways of doing stuff that are gonna increase my lifestyle and increase my ability to do stuff. I mean, it's a global phenomenon. It's just gonna explode. Yeah. You have a question? Go ahead.
Yeah, it seems to me that all this innovation has helped on the stack a lot.
There's a problem with that. With the Enron guys, Schelling and those guys, they actually talked about their attitude that about a zero sum. Like, if I can grab more, that's the appropriate ethic, business ethic, is just to get as much as you possibly can of the economy. And that was they talked about that when they were in college. And they were very Darwinian. And a lot of people in business and in life justify what they do to other people, which is not particularly moral in this sense, on a Darwinian basis. And what I'm saying is they're messing up. I mean, you can see what they did. They just grabbed all this money from us, taking all our 401k accounts and stuff like that. And are they going to be better off for that? I would argue that they're not. That they've just completely deflated our economy for a while. Now it'll come back, but all the people who were empowered to do things in their lives. I mean, some of you guys are older. Here you do probably prime life. You're really out. You're going to write that book, make that last innovation, and you're not going to be able to do it because you're going to have to go back and start pumping gas at the gas station because you can't. They steal all your money. So they disempowered a lot of people in the economy, and it's not going to be in their favor or anybody's favor to do that.
Thank you.
So yeah.
We'd like you to
So you get
have
the
this
special
gift.
the Mensa. Thank you. This is the only reason I came.
In appreciation that she made me wait until you were done to give it to you because she was afraid maybe you'd leave if I gave it to you ahead of time.
That might have happened. Yeah.
Thank you very much.